for thank you to everyone for coming to the webinar today, which is in honor of the work of Professor Nick Besley, which, as many of you will be aware, Nick was unfortunately tragically killed this summer in a cycling accident. So although this is really going to focus on his work in X-ray spectroscopy, Nick did a huge amount of work developing quantum chemistry methods and really focused on calculating things of inaccessible properties for a huge range of molecules. In the context of CONEXS, so the network for which today's webinar is organized, Nick was a huge supporter and was a great help in getting this set up and off the ground. And in fact, it's only my inability to read the EPSERT regulations for number of co-investigators on a network grant that he didn't actually appear on the list of co-investigators. And this really fed into one of his strengths of the work in this area in providing practical quantum chemistry methods that could be used to interpret and bring experiment and theory closer together in this area. And it's actually this extensive amount of work that led to me asking him if he would actually present his theory work in this webinar slot. Unfortunately, only a week before he died. So I think it's only fitting that this webinar is assigned in honor of him. At this point, I'm going to take a very brief chair's privilege and from a personal perspective. And, you know, I first met Nick well over 10 years ago when I was just finishing my PhD in Birmingham. And it's then we started to talk about the maximum overlap and the potential of it for calculating excited states. And at that stage, it was more interested in dynamics. And then we stayed in contact as we both started doing more work in X-ray spectroscopy. But aside from the work that we did together, once I started looking moving from postdoc to independent positions, he gave me some really great advice about how to kind of apply and the kind of directions. And indeed, the first grant that I was awarded as an independent investigator, Nick was actually a co-investigator at the Leverhulme Trust, and actually that funded Adam, and we got a lot of exciting results from that. So it was really great project. So back to this webinar. So we have contributions from Professor Peter Gill, Dr. Magnus, Hanson-Heine, and Dr. Adam Fouda, who have all worked in the area of X-ray spectroscopy with Nick. And they're going to describe some of the work in this area, all of which is implemented within the QCAM quantum chemistry software. And even on YouTube, there is a YouTube QCAM webinar that Nick did describing many of these methods and how to run practical quantum chemistry calculations. So if after this webinar you want to find out more, there is a huge amount of information online. So in terms of the practicalities, the usual rules for webinars. I think it's a good idea if mute mics and probably turn off videos for everyone apart from the speaker to save bandwidth. Throughout the webinar, if you have any questions for the speaker, please put them in the chat and we can ask them at the end. At the same time, in the chat, if there's any personal memories or anything you'd like to share about Nick, feel free to put them in the chat if you'd like to share them publicly. So without any further delay, I'll introduce Professor Peter Gill, who's going to talk about his work and reflections on with Nick. So thanks very much, Peter.
Thank you very much, Tom. I assume I can share my screen.
Yeah, you should.
It's working?
Yeah, looks great.
Terrific. All right, well, first of all, thank you very much for this opportunity to speak at this meeting in honor of Nick. It's a delight and a privilege for me to be able to do that. I don't have much time, but what I have, I'm going to use to reminisce a little bit about Nick's history, with me anyway, and then tell you a little bit about excited state calculations of the sort that Nick did, and then focus in a little bit towards the end on the maximum overlap method, and in particular its usefulness for studying core electron spectroscopy. And finally, some comments on Nick's legacy. So a brief history of Nick. 1999, so Tom's known Nick for a decade. I've known Nick for more than 2 decades. In 1999, there was an important double excitation in the world. And that was that Nick went from the Scripps Institute in California, and I went from Cambridge to Nottingham. So it's a double excitation. We both arrived at the same time. And Nick joined my group as my first Nottingham postdoc. Very fortunate I was to have such a postdoc. In his time with me, he was extremely prolific, signs of things to come. And this is a quick list of the publications which came out from his postdoctoral work. I've color-coded it for you just to help you see without having to read all the words, that there were already some papers which involved collaborations with experimentalists, Mike George, who I saw in today's audience, and Peter Beaton from the physics department at Nottingham University. He was doing calculations on excited states, color-coded here in blue, and making contributions to relatively early versions of the QCAM software package, shown here in shiny green. I left Nottingham in 2004 and went to Australia, I should say back to Australia. But I was delighted 3 years later to witness another double excitation, this one not involving me, but involving Nick and his relatively recently acquired wife, Elena, who both promoted themselves from Nottingham to Canberra to spend a few months as visitors in my group. And it was a delight to host them. And it was a very productive time. Actually, I should really correct myself here. It was in fact a triple excitation because Nick and Elena brought a very little Emily with them as well, which made it even more delightful. So Nick's sabbatical with me led to 2 important papers. One on this maximum overlap method, which Tom mentioned in the introduction, published in 2008. It's got 287 citations, but that number is going up quite fast. It seems to be one of these exponentially rising curves. This is one of these methods which had a slow gestation, but now seems to be receiving widespread acclaim and perhaps more important, widespread use, which is great. And the following year, Nick built on that earlier paper, publishing a second one that focused exclusively on core excited states, where an electron is excited from the core of an atom, either into the valence region or into outer space. And this one is also becoming quite well cited. Nick and Elena returned from their sabbatical, and Nick's star has been in the ascendancy ever since. I guess the sabbatical was roughly halfway along this chart that you see here. And you can see that really this was another exponentially rising curve. Nick has been doing terrific work in a number of different areas and receiving widespread recognition, both nationally and internationally, for the things that he's done. And it's a huge loss that he has been taken from us so prematurely. That curve will continue to rise, however, for a number of years to come. That is absolutely clear. So I want to turn to tell you more about these excited state calculations that Nick did so well, and just give you a quick non-technical description of them. I assume that's what would be appropriate here. So I want to begin by talking about something called single determinant wave functions. That's a scary name. I wish there was something simpler for it, but basically it's where quantum chemistry begins. We begin with single determinant wave functions. And more important, it underlies the molecular orbital picture that we all use all the time. So the notion of electrons occupying orbitals and moving around in those orbitals, experiencing the mean field of one another, is the single determinant picture, which has been totally adopted now by all chemists. So here's a picture on the left of a 4-electron system with 2 pairs of electrons occupying 2 molecular orbitals, one lower in energy than the other, and above them some unoccupied molecular orbitals. And what we do in our software packages is optimize those molecular orbitals, in this case doubly occupied molecular orbitals, to minimize the energy. That's the game that is played by the software as it crunches away, and there are lots of mathematical details behind that, of course, but conceptually it's rather simple. We manipulate the orbitals until the energy is as low as it can possibly be, and then we stop and say those are the system's molecular orbitals. Now you can easily imagine that we could consider what I'm going to call excited determinants, where you take one, or indeed more than one if you like, of these electrons and promote them from what was previously an occupied orbital into what was previously an empty orbital. And I've got 5 examples here of excited determinants derived from that first one on the left, psi0, which are all excited in different ways, but you get the general idea. And these lead one to ask, well, is there a way that we can approach excited states of molecules, because these pictures look like excited states, don't they, using this kind of determinantal approach. And the old and established way of doing this was called CIS, which stands for configuration interaction with singles. And the conceptual idea there behind CIS is that you assume mathematically that the excited state you're looking for is a weighted average of those excited determinants that I just showed you pictures of before. And that's not a bad ansatz, I guess, starting point for thinking about excited states, that it's a mixture of all those pictures that I showed you before. How would you find the weights in this weighted average? Well, you can use the variational theorem, it turns out, to do that. And that involves just diagonalizing a matrix and finding its eigenvalues and eigenvectors. So that's a conceptual basis. It used to be a widely used method. It's still reasonably widely used, but it does have some weaknesses. It particularly struggles if the excitation involved in forming the excited state involves significant changes in the shapes of the orbitals, because here the orbitals are frozen. We are occupying different orbitals, but the orbitals themselves are frozen. They are inflexible. So if the orbitals really want to change and relax during the excitation process, CIS will not allow them to do that. CIS can only model singly excited states. It can't do doubly or triply or higher excited states. And there's a complete neglect of electron correlation, which is electrons moving around trying to avoid one another. In the CIS picture, there is a method called CISD, which adds a correction which begins to account for electron correlation, but that is quite expensive, and it reduces the range of applicability of the CIS approach. Another, these days more popular approach is called TDDFT, which stands for time-dependent density functional theory. And the conceptual idea here is that we seek a photon frequency, nu, at which your molecule in its ground state has an infinite polarizability. So this is a time-dependent polarizability. So you imagine shining a laser, frequency nu, at your ground state system. The idea is that if that frequency nu has an energy h nu, which exactly matches the excitation energy, the molecule will show that by having an infinite time-dependent polarizability at that frequency nu. And you can find that frequency using linear response theory, which also boils down to another diagonalization. And so in that way, you probe directly excitation energies. This is nice and it's very popular, but again, it has weaknesses. Again, it has problems if there are significant orbital changes in the real life excitation. Can't model doubles. It struggles a lot to describe core electron excitations, which makes it particularly troublesome for the X-ray community, obviously. It also struggles to describe charge transfer excitations, Rydberg excitations, and conical intersections. And these are actually not a series of different weaknesses. They are actually manifestations of the same fundamental weakness, which I won't go into here, but there's one core problem with TDDFT, which manifests in a number of different ways. What Nick was involved with from his sabbatical with me onwards was what are known as DeltaSCF methods. They have a different conceptual basis. And the idea here is that we say, well, molecular orbitals minimize the energy of a ground state system. What about molecular orbitals which don't make the energy minimal, but make it stationary? So it's flat, but it's not minimal. In other words, that's a saddle point of the energy. What could we do, if anything, with those molecular orbitals, a set of molecular orbitals which make the energy not minimal, but stationary, a saddle point? Those saddle points turn out to be legitimate solutions to the mean field problem. That means the electrons are moving around and still moving in the mean fields of one another. But does this system have a physical interpretation? And the early 2000s, Dr. Andrew Gilbert, who was working with me, conjectured that these saddle point solutions correspond to excited states of the system. So this gives us a pathway, if the conjecture is correct, to finding excited states by doing self-consistent field calculations. These are not CIS, these are not TDDFT, these are just boring old SCF calculations like Hartree-Fock calculations. Now, two questions which are commonly asked when this proposal is raised, and in fact, I asked these two questions of Andrew when I first heard this conjecture, is, aren't these saddle points difficult to find? Our programs, our software usually hunts for minimum energy solutions. And how are we going to tell the software to hunt for some higher lying saddle point solution? And the second question is, isn't it true? It's certainly the conventional wisdom that most excited states have multi-determinant character. That means you can't really model them at all well with a single determinant with excited electrons. They need more than one determinant mixed together. If that were true, then a single determinant will model an excited state poorly, and this will give an uneven treatment of excited and ground states. That would not be good. Turns out the answer to the first question is no, these aren't difficult to find. And the answer to the second question is, don't most excited states have multi-determinant character? Is no, most don't. A few do, but most don't, which is good news. So now, in my last few minutes, I'm going to zoom in on the maximum overlap method in which Nick was a pioneer. The governing principles here are as follows. The ground state molecular orbitals are usually not optimal for describing excited states. Excited states tend to be more diffuse. The system is more diffuse, and so it wants orbitals that are more diffuse to capture that changed character of the electronic structure. So it's obviously better, if you can, to optimize the molecular orbitals for the particular excited state that you're interested in. The problem from a technical point of view is that the algorithms that we've used in the past always tend to collapse down to and re-find the ground state. That's no good. We need some way of avoiding that collapse down to the ground state if we want to find an excited state. So the maximum overlap method, as it was originally introduced by Andrew Gilbert, Nick Besley, 2008, achieves the objective by saying what you need to do is make very high quality guesses for the occupied molecular orbitals in the excited state, not the occupied molecular orbitals in the ground state. That's relatively easy, but you need to be able to guess pretty well what the occupied orbitals in the excited state look like. And once you've made those high quality guesses, you then have to ensure that in the iterative self-consistent field process, as you go round and round, refining the orbitals, making them better and better, that they change as little as possible from one cycle to the next to ensure that you stay close to those high quality guesses. And we use a criterion of changing as little as possible, which boils down to the new ones overlapping as much as possible with the previous ones, which is why this is called the maximum overlap method. I should just mention that more recently we've developed a a child of the maximum overlap method, which perhaps confusingly we've called the initial maximum overlap method. It's not the original, it's the second one, but we call it the initial one. And if you look at the recipe, you'll see it's extremely similar, but the IMOM method on each cycle of the SCF ensures that the new molecular orbitals resemble the initial guess, that high quality initial guess, as much as possible. It's a subtle variation on the original maximum overlap method. MOM has some strengths, which is why I'm talking to you about it. It also has some weaknesses. So strengths, relevant ones here, are that you can apply it to study doubly excited, triply excited, quadruply excited states. You can apply it to core electron excitations, and it works well. It works well also for charge transfer excitations, Rydberg excitations, and even conical intersections. These are all in my list of weaknesses for TDDFT. So the MOM approach helps us to overcome those, or to avoid those TDDFT weaknesses. Weaknesses of MOM itself are implicit in the methodology, really. You do need a good initial guess for the occupied molecular orbitals of the excited state. And Nick and Andrew have worked hard on heuristic ways of obtaining good initial guesses for excited state occupied orbitals. But even if you manage to find your excited state using MOM, normally it's very spin contaminated. Now, I'm not going to go in here to what that means. If you know what it means, good for you. For many purposes, it doesn't matter. But if you are interested in spin sensitive properties, a strong example would be NMR, for example, NMR of excited states. A spin contaminated wave function is not going to be one that will give you good results. So that is an important weakness of the MOM approach that you need to be aware of. And it is true that some states of some systems are poorly described by a single determinant. If you happen to want such a state of such a system, probably MOM is not the right tool for you. Well, here's some pictures of the key players here: Andrew Gilbert, Nick Besley, and Giuseppe Barker. Giuseppe did the more recent IMOM method a couple of years ago. A bunch of very smart guys. It's been a privilege having these guys as collaborators. I so enjoyed working with all three of them. And again, it's such a loss to have said goodbye to Nick. All right, so how do you do a MOM calculation in the QCAM package, for example? Just a very simple example here. If you wanted to do a calculation of this excited state of the beryllium atom, where we've taken one of the 2s electrons and promoted it into the 3s orbital, what you do is, first of all, you do job 1, which is a ground state calculation. That gives you the molecular orbitals that you can see in this little table, numbered 1, 2, 3, 4, 5, 6, 7, 8, 9. And what we want to do is promote an electron from molecular orbital 2 into molecular orbital 6. That will achieve the excitation that we're interested in. And at the bottom half of the slide here, you can see a part of the QCAM input. The most important part is the second to bottom line, where you specify to the software, I would like to promote an alpha electron, that means a spin up electron, from orbital number 2 into orbital number 6. That's all you need to say, really. And then the software will go ahead, do that promotion, obtain a guess for that excited state, and then iterate around to refine those orbitals and finally give you the single determinant description of that excited state. For core electrons, which that previous example was not, the energies, of course, are much, much larger, as you all know better than I do. And there are two important pictures, scenarios. One where the electron is promoted from a core orbital into a valence or Rydberg orbital, and the second scenario where it's evaporated completely from the system and goes to the end of the universe. That's a proper ionization. Those two create respectively an excited state of the system, which I'm going to indicate here with M star, or a cation of the system, M plus. So these are respectively a highly excited state of the neutral, or a highly excited state of the cation. Both of them are highly excited states because they've both got a core hole left behind. Here are some results which I snagged from that paper that Nick published in 2009, just some random organic-y sort of molecules. We're exciting a core electron from the bold atom in each of these molecules, got the experimental core electron binding energy here to 2 significant figures in electron volts. And then I've got the error if you use Nick's approach to do this using the B3 lip functional and using a variant of the 6311's G star basis set, whatever that is. The important point here is that the errors in these CEBEs, core electron binding energies, are usually a fairly small fraction of 1 electron volt out of a total excitation energy of 300 or 400 or 700 electron volts. Very encouraging, and these calculations also are very inexpensive, so you can run them on your laptop while you are sipping a latte. My final topic is Xray spectroscopy, just for a little bit of change. In Xray spectroscopy, you ionize a core electron, next to core electron falls into the hole and ejects perhaps a valence electron as a result. So there's quite a few electronic movements going on. The end result is that you have a system with 2 holes, one in this case that I'm showing you here, which is a neon atom, one in the 2s shell and another in the 2p shell. And you could use the MOM approach to study the energetics of this. Job number 1 on the left-hand side of the screen here is a QCAM input file to do a calculation on the ground state of the neon atom. That's rather straightforward. And then on the right-hand side, we are doing a calculation on the neon dication because it's lost 2 electrons. Which 2 electrons has it lost? Well, you can see from the second to bottom line here, in this block of numbers here where I say which orbitals are occupied, you can see obvious holes in orbitals 2 and 5 because we have removed 2s and a 2pz electron from the system. And here are the results that you get. I'm not going to go through these, but these give you the energetics of the Xray processes which are involved. So I think my time is up. I just want to say very quickly that Nick's work in this area on excited state solutions has been picked up by mathematicians. Mathieu Levin is a French mathematician, published a paper a few years ago where he pointed at our work and said that probably single determinant approaches have been underestimated. Their power has been underestimated in the past. So what's Nick's legacy? Well, a lot of the things that he has invented, he and his group have been implemented in software which you can access through the IQMOL graphical user interface. That's an interface produced also by Andrew Gilbert. At the heart of the matter, Nick's code is implemented in the QCAM package, and Nick has been contributing to that package for 2 decades, which is quite extraordinary. We are enormously grateful to Nick and his team over the years, and as a result, the QCAM board of directors decided that they would create a new award. You can go and read about it at the qcam.com website /about/Besley. I won't read this to you because you can read it faster than I can speak it, but we have established this to recognize excellence in the development of new methods for computational spectroscopy, which is obviously Nick's primary but not sole claim to fame. And here, my last slide is a page from the QCAM website, which just provides some details about Nick's background and about the award. And thank you very much for listening to my story.
Okay, thank you very much, Peter, for a fantastic talk, and it's great to hear about the Nick Besley Award. I hadn't heard about that, so I think that's fantastic. So very quickly, if anyone had any quick scientific questions about the talk, got a little bit of time before we move on to the next speaker. Feel free, just to reiterate, if you do have any questions, feel free to add them in the chat. I'm sure if we start the next talk and a question comes to mind, then Peter will be happy to answer this in the chat. So thank you very much. Okay, if not, we'll move on to, oh, there's a question from Felix. I'll ask very quickly. So from Felix Placer, I was wondering if there was a simple way to tell under what circumstances MOM works.
No, there isn't, Felix. This is one of these things which is as much art as science. So you build up experience and you get to be able to tell the telltale signs when things aren't working. But I can't give you, unfortunately, a formula that will tell you. It's actually like most of the methods in quantum chemistry, that we never know for sure what their errors are.
Thank you very much. Okay, so now if we move to Magnus, who for many years was a postdoc of Nick's, and he's going to present some of the work they did together. And so over to you, Magnus.
Okay, thank you. Just let me share my screen quickly. That's lovely. Okay, hello. So my name's Dr. Magnus Hanson-Heine, and I'm a former PhD student of Nick's and longtime collaborator at the University of Nottingham. Today, I'd like to share with you two methods in the calculation of Xray emission that Nick and I worked on together. And hopefully this will give you some kind of insight, although limited, into that quiet brilliance that really characterized the man. The first of these is to talk about short-range corrected functionals in density functional theory. X-ray emission, very quickly, is the absorbance of an X-ray photon creating a core hole through ionization, and then you get X-ray emission as occupied orbitals drop down and fill that hole. Very briefly, I'm going to talk about self-interaction error. This is work that Nick did on his own, but it's a precursor to what we did together. When you look at Hartree-Fock theory and electronic structure calculations within that framework, what you have is partitioning of the electron-electron interactions into two bits. A mean field term where the electron density repels itself, and then an exchange term where the energy is lowered. What you find when you have a one electron system, though, like the hydrogen atom, is something quite interesting. So there's only one electron, there's no electron-electron repulsion there, but there's still an electron density associated with that one electron, which means in that first term, the electron density effectively repels itself. And then you get exchange, and that electron undergoing exchange with itself exactly cancels that energy to zero. This is a mathematical artifact of that approach. It's exact for Hartree-Fock theory. But when we move to density functional theory, which is probably the workhorse of quantum chemistry still, we now have approximate forms of exchange. This means that that cancellation is no longer exact, and some of the error you get in DFT calculations is therefore, well, for lack of a better term, an electron or the electrons in your system interacting with themselves. This is usually fine and quite a minimal error, negligible for all intent and purpose, because the surviving density functionals like B3-lib and the ones commonly used do a pretty good job, and they're well parameterized for electrons that exist within, let's say, average bonding distances of each other. So that cancellation more or less is complete. However, there are a few instances in the literature where that's not the case. The most well-known of these is for charge transfer excitations within time-dependent DFT. That's where an electron is promoted across a large spatial distance, and therefore you fall outside of that common and well-parameterized, let's say, average bonding distance for your electrons. This is most commonly fixed in the literature by a process either called long-range separation or Coulomb attenuation, giving functionals, the most famous of which is probably CAM B3 lib. And that approach is to partition the Coulomb operator again into a long and short range component and simply add in more exact Hartree-Fock exchange at the long range. This fixes up the problem pretty well. Nick's insight here really was to note that there's another case where this kind of approach might be applicable. And that is when you look at core orbitals, which are obviously very important for X-ray calculations, because the 1/r² relationship, essentially the closer you are to the nucleus, the more attracted those core orbital electrons are. And that attraction, for lack of better phrasing, forces them closer together with other electrons, and again, outside of that parameterization distance. And these electrons that interact at short ranges, again, have a self-interaction error problem. So Nick's approach, elegantly, but showing quite a deep understanding of the theory and the problem, an intuitive one, I'd argue, was simply to say, can we take that existing range separation approach, that long range separation, and just reverse it so that by parameterization, we now essentially add Hartree-Fock exchange, exact exchange in for these short range interactions, and to see what would happen if that was done. In doing that, he created the so-called short range corrected functional, or SRC as an acronym, with some modifier suite of density functionals in density functional theory. And what we see when you apply a short range corrected functional, moving from a sort of standard one, is sure enough, your core orbitals and their energies are significantly affected, but the valence space and the bonding orbitals remain more or less unaffected, which gives you reasonably good chemistry, chemical properties at the same time. So this is where our work together sort of jumped in, which was, now that there's this method for calculating more accurate core orbitals, what does that look like when you apply a maximum overlap method based way of calculating core ionization, or ultimately core emission, or X-ray emission? And what you find is the reflection of the error in that first column there, where for K-edge calculations using B3 lip, which is one of the most well-used and well-known functionals in DFT, you have an error of about 40 electron volts. And that error really drops to 1 or 2 electron volts when you apply this short-range corrected functional type. So this is what that actually looks like in terms of spectra. These are very simple calculations based on 2 self-consistent field density functional theory calculations, one using the maximum overlap method, which you've just heard about in detail. What you can see is, for this very cheap and straightforward type of calculation that you can really apply to extended systems like nanotubes, due to its low cost computationally, you get pretty good, I would argue, matching with experiment. The degree of the match here is actually better than a quick glance at these spectra might imply, because those starred black peaks are actually multi-ionization processes that weren't taken out of the experimental data. And the few cases where there's arguably clear shift between the red and black lines, they tend to correspond to things like phenol or methanol, where there's a rotor. And obviously in the experiment, you have a dynamic system, which means you'll have conformational averaging as that rotor goes around, whereas in the DFT calculations here, they're static based on the optimized geometry of the system. And sure enough, in this case, these calculations use RIX, which involves, rather than core ionization, excitation of that initial core orbital, with the red and black lines being different initial excitations. This shows methanol and really illustrates that point. So for the experiment at the top there, you have 2 excitations which have different intensities in terms of their X-ray emission, but are more or less superimposed in terms of peak positions. Whereas when you use static DFT based on a single structure, you can see that those 2 excitations no longer have identical positions. When you add in dynamic averaging from snapshots of molecular dynamics trajectory, though, you can see that you start to get something that better matches the experiment again. So it's expected that that can be used as a method to further fix up and improve the spectra you just saw in the slide before. Okay, so the second thing I'd like to talk about is the development of basis sets that are specific to modeling core hole excited states. This work was really motivated by examination of basis set convergence, and that is as you increase the electronic basis set size, which is you can think of loosely as sort of the pixel resolution of your wave function as you implement it on a computer. As you go to higher resolution, larger basis sets, you get, for the ground state, rapid convergence. So most noticeably for the hydrogen chloride molecule at the bottom there, the 631G star basis set at the top is a very small, compact popal basis set. The basis set's constructed essentially out of atomic-like orbitals based on the hydrogen atom with some parameterization. So that gets about 1.5 electron volts of error compared to a very large basis set, which is taken to be converged. And by the time we move to a sort of intermediate size, which is denoted there as CCPVTZ, which is a member of the Dunning family of basis sets, that's usually considered reasonably converged for DFT purposes. And the error drops down to about 0.2, 0.16 electron volts of error, or I misread the column, so 0.28 there. This is low error converging rather rapidly for ground state calculations. When you do a core ionized state calculation, particularly for those second row atoms, you find for HCl, though, there seems to be a qualitative error. There seems to be something missing from those basis sets. So 631G star gives 20 electron volt error. And when you move to CCPVTZ, which is reasonably converged for most applications, for HCl, the error is actually larger. It's now 30 electron volts. So you have a very large issue in terms of error creeping up at the start with normal basis set parameterization, and it doesn't seem to be converging, at least not in any systematic way. That error doesn't go away for larger basis sets. So this is an interesting thing to note. There are really two exceptions that we found for this. The first is this so-called CCPCVXZ family of Dunning basis sets. Those have specifically parameterized core valence basis functions to address this problem. These are very large basis sets. They do cover most of the periodic table, but if you wanted to calculate an extended system, like a nanotube, say in an even-tempered way, this would not be possible. They're quite prohibitively expensive as your calculation scales up in size, and that can be a problem. The other instance where this seems to have been solved by happenstance, I believe, is the so-called IGLU or IGLO family of basis sets, which are two basis sets, one of double and triple zeta quality, which were parameterized for NMR. And something in the NMR parameterization appears to have gone and fixed or accurately described something about the core region. This is great, except the IGLU basis sets have only been parameterized for a few atoms, so HCNO, maybe fluorine and one or two others. But that means they don't cover the bulk of the periodic table, certainly no transition metals, which really, at the time we were working on this, left a huge hole in terms of if you wanted accurate calculations, especially for extended systems that involve transition metals. There was essentially nothing out there in terms of basis set that would really do that for you. So Nick's, again, insight, or I suppose initial question, conjecture is a good word, was to simply note that in the first instance, maybe in terms of average potential at least, if you remove an electron from the core region of a molecule or an atom, that might be similar in terms of that average charge to adding in a proton. And therefore the question was, well, put simply, what would happen if we take the basis set for, so the atomic basis set for the next atom along in the periodic table and add those basis functions in to either the core region or the whole basis set for the atom you're interested in. This is the so-called Z+1 approach here. And in answering that question, what we find is that, sure enough, it does actually seem to solve this problem very elegantly. So let's look at here, we've got some second row atoms. For the MP2 values on the right-hand side there, for this very small 631G star basis set, you've got an error of about 17 electron volts. And sure enough, that gets corrected 2 rows down by applying this Z+1 approximation, where you just mix in those other basis functions from the next atom along. You find that the error drops to about 0.18 electron volts. So that's effectively fixed up that large qualitative error. This is what that looks like in terms of actually the wave functions produced for these orbitals. So these are for SiH4, and they show the 1s, 2s core excitations from the silicon and the highest occupied molecular orbital. The top there is for this very large quadruple zeta core valence Dunning basis set, which we can more or less consider as accurate. You see 2 features that are worth mentioning. The first of which is that it rises to a nice asymptotic point. The exponential rise there is captured by a nice clear cusp at the nuclear center, certainly for those core orbitals. But the second point really is that the core ionized state in red actually has a higher wave function amplitude at the core. And this higher and indeed lower amplitude is also there for the highest occupied molecular orbital. So it really does seem to propagate through the wave function as a whole. When you look at 631G star in the middle, and this is true for those other commonly parameterized base sets that don't have core valence functions in them. For starters, you don't have enough Gaussian functions. It's a small basis set, so you don't have the resolution to really capture that exponential rise. But the most noticeable thing is that the excited state from the core and the ground state more or less have the same wave function amplitude. So that looks like the thing that isn't being captured here. And sure enough, when you add in the Z+1 approximation, you still don't have enough Gaussian functions, enough resolution to capture that exponential rise properly. But you do get the difference in amplitude back. And that really seems to be the sort of wave function based expression of this problem. So here's what that actually looks like in terms of transition metal complexes. So this is probably the most interesting bit here of this talk, in the sense that these kind of systems, especially as you move to larger and larger ones, although these are reasonably small, sort of middle size, depending on your definitions there. As you move down the rows of the periodic table, this error becomes larger, it would seem. And these calculations previously were starting to become inaccessible, right? So you could have used those CC core valence Dunning basis sets, but the size of your calculation would start to become prohibitive. However, with this Z+1 approach, what it enables you to now do is effectively use any basis set that exists already, any pre-existing basis set, from a minimal basis set right the way up to the larger ones, of which many basis sets have been parameterized over the years, and simply modify them now to cover the entire periodic table, bar the last atom they're parameterized for, and therefore open up the space dramatically as to the type of system that can really be accurately studied in terms of looking at core ionization. So for transition metals, you see a range of errors here, really ranging from about 10 electron volts to about 70 for TIF4 there. And even for this very small basis set, you can see the errors drop down to about 1 to 3 electron volts when you add in this Z+1 approximation. And it's worth noting that probably some of that error in that final calculation is just going to be due to the fact these basis sets are quite small anyway. Right, well, without further ado, I suppose I'd like to thank Nick fundamentally and very profoundly for just an unbelievable amount of support and help. And to say you'll be sorely missed is a profound understatement. I'm sorry you're not here with us today. I think I'll leave it there, but obviously QCAM and the universities and CONEXS are all very much thanked too.
Thanks very much, Magnus, for a really great talk and your reflections. So I have time for one question, and Felix has has asked another question. So could you comment a bit more on the range separating parameter for short range exchange? What's the length scale involved? How do you get the parameters, and how transferable are the parameters?
Thank you for that. So that's work I didn't explicitly do with Nick, so I might not be able to answer that best for you, other than to refer you to the paper. In terms of the initial parameterization, I do know that there are several of them in that family with slightly different parameterization. So it appears that effectively a different functional parameterization per row on the periodic table more or less captures a sort of average parameter set. So there's effectively a first row set and a second row set. So a first row functional and a second row functional. There was some work on an Xray emission specific functional, but I think in the end, like with SRC1, which is one of the originally parameterized ones, does a reasonably good or equivalent job when looking at a large range of systems. So they seem to be reasonably transferable, but again, as you go down the rows of the periodic table, you do need to change the parameterization somewhat.
Okay.
Well, second part of the question, or just that answer?
No, I think you've answered the question. Thank you. Brilliant. Thank you very much, Magnus. So now for the final talk, we will move to Adam Fouda, who, as I said at the start, was a PhD student for Nick, funded through a grant that we had together, looking at time-resolved X-ray spectroscopy. And his work during the PhD went far beyond that, and he did many different areas. And so he's going to talk about some of that today. So yeah, over to you, Adam. Thanks very much.
Thank you for the introduction, Tom, and thanks for giving me the opportunity to speak today about the work I did with Nick. So I was Nick's PhD student from 2016 to 2020, and we did a few projects in X-ray spectroscopy together. This is just a bunch of his graphical abstracts that I've taken here. So I'll start by just giving an overview of Nick's contributions to X-ray spectroscopy, and then some of the early developments that he did that we've already heard about from Peter and Magnus, so how they kind of enabled the work that we did together. And then the three projects I'll talk about are basis sets for core electron spectroscopy calculations, TDDFT for Xray emission spectroscopy, and resonant inelastic X-ray scattering calculations. Just so people have an idea of the kind of processes that we'll talk about, here's some schematics. This is X-ray emission spectroscopy, where electron goes into the continuum, and then what you detect are the X-rays emitted when occupied orbitals collapse to the hole. And X-ray absorption spectroscopy is just in the kind of the near edge sense is when you kind of excite a core electron to virtual occupied orbitals. And then resonant inelastic is X-ray scattering, is where you look at the X-ray that comes in and that excites to virtual orbitals, and then the inelastic scattering that occurs when occupied electrons collapse to the core hole. So I fit all of Nick's corresponding author papers onto one page. It was a bit of a struggle, but we got it. So this is all the work he's done. There's also another 10 non-corresponding author X-ray spectroscopy papers. And I should mention the 97 other computational X-ray spectroscopy papers he's done that kind of cross the electromagnetic spectrum. And some of his kind of other areas of focus were looking at like vibrational spectroscopy of carbon nanotubes and fullerenes with IR, and also UV spectroscopy of surface absorption were some of his other strong areas. So these kind of purple ones are the kind of early development stuff I'll mention briefly, and then the kind of papers that I will be talking about that we did together, and some of the other related ones that are down here. So, and I think it's better in his own words. So I think Tom mentioned there's a QCAM webinar, but there's also these 2 review papers that he published recently. where he kind of summarizes his developments and his work in DFT calculations for X-ray spectroscopy. Initially, Nick kind of implemented TDFT in a reduced single excitation space for valence excitations in solutions and on surfaces. So he just implemented this method into QCAM, and then this kind of approach where you can pick which orbitals you excite from is actually very useful for X-ray spectroscopy, because you can select a core orbital to excite, and you can go straight to your core excited states without having to compute the whole spectrum. And he then first applied this to X-ray absorption spectroscopy of molecules absorbed onto silicon surfaces. And then, as Peter has nicely explained earlier, the maximum overlap method that lets you get excited state wave functions that Nick kind of took to the core excited state regimes. This has become a very ubiquitous tool for X-ray spectroscopy, as it lets you generate core ionized reference states that you can then use for X-ray emission spectroscopy calculations. And there's another application that's kind of appeared a lot recently, is using it for transient X-ray absorption spectroscopy of valence excited state dynamics. So you can generate a valence excited state reference state that you then use in your TDFT core excitation calculation. This is one paper that we did together, and there's a few other studies out there using this approach. And Magnus nicely explained this in the previous talk, is the short range corrected functionals that they kind of correct the self-interaction error problem for short range electron interactions, and it kind of gives you correct core orbital energies, well, reduces the core orbital energies, and that allows you to you don't have to shift TDFT spectra anymore. So if you're using a standard hybrid functional like B3LIP, you'd have to kind of like apply about 10 eV shift to align the spectra to experiment. But with these short range corrected functionals, you no longer need to do that. It kind of gives you agreement straight away, which makes the TDFT quite a good predictive tool for X-ray absorption spectroscopy. And then, yeah, Nick was also applying this to Xray emission spectroscopy. And we did some work where we tried to kind of reparameterize the functional so you don't have to shift it. And he was also looking at using these functionals to calculate accurate core electron binding energies of heavier elements too, in his most recent work. So looking at the basis sets for core electron spectroscopy, this kind of started with Nick had the idea that, well, he saw that people were typically using basis sets for core electron spectroscopy that you use for valence electron spectroscopies. And these basis sets wouldn't really describe, they won't have many functions for the core orbitals. But he saw that basis sets designed for NMR calculations actually did have a lot of functions for the core orbitals, because it's important that you describe the orbitals around the nuclei in NMR calculations. So we did a benchmarking study where we kind of screened a lot of basis sets, so the UGLO 2 and 3, and these PC capital S seg basis sets are ones that were designed for NMR spectroscopy. But we scanned all these across these molecules, where we looked at the first and second row of the S&P block. Then we did a DeltaSCF calculations using MOM of the core electron binding energies and also the first core excitation energies. And then also looked at TDFT for Xray emission spectroscopy from a core ionized reference state, and also TDFT calculations of Xray absorption spectroscopy from the ground state. So Nick was right. The NMR basis sets did perform really well. So here on the y-axis is the maximum average deviation with respect to this PCS seg4 basis set, which is a good approximation to the basis set limit. And on the x-axis is the measure of the basis set size. And you can see these kind of PCS seg3 and IGLU ones are doing the best in terms of the reduced size and reduced errors. And you got a similar result if you kind of used a correlation consistent basis set as your approximation to the basis set limit as well. So the errors that you got from the smaller basis sets and the basis sets that don't describe the core well, it comes from a poor description of the core ionized state and not the ground state. And Magnus touched on this in his talk. In order to kind of accurately describe core electron binding energies with DeltaSCF methods, you need a basis set that is flexible enough to kind of deal with the orbital contraction that occurs when you remove an electron, and that can be shown in the radial behavior of the wave function. So the PCS-4 represents the kind of correct answer at the basis set limit, and then you can see the igloo is closer in terms of the height of the peak and its sharpness when you're describing the wave function about the core. And then the ones that do poorly have this kind of broad low value to it. So this kind of what we saw here with the core electron binding energies, it also applies to X-ray emission spectroscopy with TDDFT, because there you do have a core ionized reference state relaxed with MOM, where this applies. But this doesn't apply to ground state X-ray absorption spectroscopy TDDFT, because the description of the ground state orbitals from your basis set doesn't affect the quality of results. So you can use valence heavy basis sets for ground state X-ray absorption spectroscopy. So it was nice that we could straight away just apply what we found to interpret some experimental data. So we kind of use this to interpret XPS spectroscopy on ionic liquids, and our calculations, we chose this PC-SEG2, which is quite a moderately sized basis set for these kind of ionic liquid structures, and we could accurately calculate the chemical shifts that occurred when you change the functionalization of the anion part of the ionic liquid, and it worked well to kind of interpret what they observed in the experiment. And then, as Magnus has spoken about, the kind of continuation of this was the development of the Z+1 basis sets, where you kind of supplement your basis set with functions from the element of the next highest nuclear charge. And so these have, as we have seen, have provided really a kind of efficient and accurate approach to calculating core electron spectroscopy. And one of the applications of this was looking at the kind of valence to core X-ray emission spectroscopy of halozincate complex ionic liquids, which was another experimental collaboration that Nick did with Kevin Lovelock, and their results showed they kind of demonstrated the local nature of X-ray emission spectroscopy, as Nick's calculations showed there was only a small change between the kind of the anion surrounded by the cations and just the anion on its own, which shows that when you're kind of probing at the zinc, which is at the center of the anion, the presence of the cations have a small effect on those orbitals of the occupied orbitals involved in the X-ray emission spectroscopy. And these calculations also kind of determined that the X-ray emission spectroscopy was happening from a localized core hole rather than a delocalized core hole, because the shift that you get with the delocalized description just didn't kind of agree with what they saw in the experiment, but the localized did. And then so his latest work, which I mentioned before briefly, so I think, you know, the basis set problem is kind of done here. So he was looking at moving on with DFT. The next thing you got to deal with is the functional, and because the problem of the self-interaction error gets worse when you increase the size of the nucleus where the core hole is at. So the kind of the approach here was to try and correct the self-interaction error for the second row P block with this short range corrected exchange correlation functional. So kind of it performed well, but not great. So he wanted to improve the experimental accuracy of his functional. And there was two approaches to this. So he did elemental specific energy shift for each of the functionals, which you kind of need a data set to kind of determine. And then the other approach was then to reparameterize this functional to remove the core electron self-interaction error. And it was seen that the second approach matched the accuracy of this first approach, showing that you can, with this kind of short range Hartree-Fock description, you can kind of circumvent the requirement to calibrate an energy shift from a data set, which was a promising result. And it's a shame he couldn't go further with this work. But so going on to X-ray emission spectroscopy. So they're using kind of can-be free lip functional with the Z+1 basis sets. They could show that they could accurately reproduce the experimental X-ray emission spectroscopy spectra of diglycine if they applied a 6.6 EV shift to it. So then they kind of carried this forward to these, Alexandra and Nick carried this forward to these secondary structure proteins. And they could, this approach was efficient enough to kind of calculate these structures. But, you know, they had to kind of calibrate a shift to apply to it first. So part of the work that me and Nick did was kind of like to think, can we kind of get around having to apply this shift for X-ray emission calculations with TDDFT? So you can go down the route of increasing the portion of Hartree-Fock exchange for the short range electron interactions. But when you want to actually compute the emission spectra, it kind of ruins the spectral profile of it. So we had to think of another approach. And so we kind of, we know that if you do DeltaSCF with DFT, you get good experimental agreement with X-ray emission spectroscopy energies. But you know, this approach is very time intensive in terms of like the work you have to do for computing large systems, because you have to do a separate calculation for every emission. But we can actually use these kind of accurate DeltaSCF energies to calibrate the shift for the TDFT spectra, where you can compute the whole spectrum in one calculation. And that's what we did. So we would take the kind of HOMO to core a DeltaSCF value for a range of molecules, and then use those values, and then use the shift from those values to the first HOMO to core TDFT calculation to shift. And then we have a kind of purely computational way of aligning the spectra. And then now we can kind of, here you can see the agreement is pretty good. So we can kind of predict X-ray emission spectroscopy calculations for systems where we don't have any kind of prior information about using this approach. So on to resonant elastic X-ray scattering. So Magnus touched on this. They kind of looked at these kind of using CONEXS DFT to kind of compute emission spectra from the orbital energies and the kind of transition dipole moment between the orbitals, and found that using the kind of core excited state nuclear dynamics from maximum overlap method and ab initio molecular dynamics methods kind of improves the spectra. He kind of improves the peak heights and the positions. So we kind of wanted to take this forward into calculating these resonant inelastic X-ray scattering maps. So we have the excitation axis on the Y, and then the emission axis on the X. So we're looking at both the photon in and the photon out process here. So we kind of use this DFT with the maximum overlap method and ab initio molecular dynamics to kind of produce these maps using intensities that were taken from the Kramers-Heisenberg formulism to try and recreate these maps. And we found that it worked. It only works if you sample the dynamics. So as you can see here, the MOM ab initio molecular dynamics method not only does it kind of correct the broadening, but sorts out the intensity distribution between the two intermediate states with respect to the experiment. And that kind of comes down to how sensitive the orbitals involved in the emission step are to the nuclear motion. So you can see these bond lengths are really small changes in bond length here. And you can see that the 1b1 is the non-bonding orbital in water, and which lies perpendicular to the nuclear axis, and it's not that affected by sampling the dynamics. However, the 1b2, which lies in the plane of nuclei, is much more sensitive, which is why we see this nice broadening, and we get this kind of increased intensity of the 1b1 peak here for the 4a1 state. So then moving forward, we did another RIG study. So we worked to interpret the experimental RIGS map of nitric oxide. Here we couldn't use DFT-based methods, single deterrent methods anymore. It's because nitric oxide is a open shell in its ground state, and its excited states have a strong multi-configurational character to them. So we used RAS-PT2 methods, and we saw that in this red zone, there was these kind of states that we didn't expect, and these are these kind of like doubly core excited states. So where like a 1s has gone into the pi star, and then a pi has also got electrons also gone into the pi star states. So that, this happens in X-ray, like XPS and Xray emission spectroscopy. It's like shake-up states, and you can see they appear here in the Xray emission spectroscopy. So Nick did these calculations with you on CCSD, and you can see that these, where you have ionized, when you've got a valence excitation accompanying the core ionization, they appear in the Xray emission, but they appear at much lower intensities with respect to the single electron processes than they do in the RIGS maps. And then in the RIGS maps, they also have this very striking vertical broadening feature. So our kind of potential energy surface calculations showed that these double excited, core excited states have quite a dissociative potential energy surface character to them. And I calculated this map again at a much lower, a longer bond length, and we actually saw this kind of peak, which corresponds to this peak in the experiment. We saw that kind of vertically drop in energy too, which gives us an indication that there's some dissociative process going on potentially. And it was interesting that kind of these at the Frank Condon region of the ground state, there's near degeneracy between these double excited states and the Rydberg excited states, which contribute to the features in the orange box here. So there's still some kind of questions to be asked here about this. Yeah, as I said at the start, Nick has his own kind of review of a lot of the work that he's done in X-ray spectroscopy with DFT in these two review papers. And an interesting development that was happening in the group done by Steve, Mason, Peter and Nick was the kind of the airbed method. And what this method did, it was kind of, it vastly reduces the cost of 2D surface DFT calculations using a kind of a point charge model with a dispersion correction. And this is a really good tool for Fizzy absorption onto 2D surfaces. And I think it's something that could be very useful for X-ray spectroscopy too, at reducing the cost of calculations. So yeah, I just kind of big thanks to Nick for being a great supervisor, someone who would always kind of value everything you had to say and respectful. And, it just wasn't doing research with a supervisor. It was like doing research with a friend. And I think I say for all the postdocs and PhD students that work with him, that he'll be forever missed. Thanks.
Thank you very much, Adam, for not only the scientific presentation, but also your reflections as well. That was fantastic. Thank you. If anyone has any questions for Adam, they can put them in the chat. I know we're already overrunning, but I don't really, time is not important today. just give it a minute or so, see if there's any questions. If not, Adam has very helpfully put his email address at the bottom here. So if you end up with any questions, then you can always send Adam an email afterwards.
Yep, my Argonne one should be active again next week, but for this week I have.
Okay.
No.
Okay. Yeah, the joys of moving.
Yeah.
Okay, well, in that case, this brings this webinar to a close. So I think first of all, I have to thank the speakers for so fantastically describing both the research and their reflections on Nick and the contributions that he made both to science and to them. And the one thing that reminded me is that, the breadth of work that we've covered in this webinar, and it only focuses on his area of X-ray spectroscopy. This really shows the kind of the breadth of work that he did and the impact that he made in X-ray spectroscopy. Secondly, I'd like to thank everyone here for coming. This is by far and away the largest turnout we've had for a webinar, and I think that's only fitting. And again, demonstrates both the influence that Nick had, both as a researcher and a person. Thank you for everyone for coming and the speakers again, and I wish everyone a great rest of the day. Thank you very much.